In this video, we're going to be figuring out the product distribution of radical chlorination of an alkane that has primary, secondary, and tertiary hydrogens. And the alkane is 3-methylpentane. So that is this alkane here. The bond line formula, I find it's a little bit more convenient to represent it using that is this. And we want to know what happens when this reacts with Cl2 and is irradiated so that the chlorine radical can actually be furnished. Because remember, mix these two gases. I believe this is a gas at room temperature. If you mix both of them, they're not, nothing's going to happen. But when you add UV light, you will get a reaction because the Cl2 will split up into two Cl radicals. Well, anyway, you'll get a mixture of several products here. So you could, well, let me go ahead and label the carbons. This is C1, this is C2, this carbon here is C3, this is C4, this is C5, and this carbon here is C6. So you could have chlorination at C1, but hopefully you see that's the same as having chlorination at C5. Either of those will give you this product here. Alternatively, this should be Cl. I know it looks like something else, but here, I'll just rewrite it. You could have chlorination at either C2 or C4, but those would be the same as well. So they'd be different from this chlorination, but they'd be the same as each other. So you get this product. Alternatively, you could have chlorination at C3, which is the tertiary carbon here. Remember, there's a hydrogen sitting here. Carbon makes 4 bonds. There's a hydrogen. It'll be abstracted to form the radical, and then chlorine will attack here. So you will get this compound here. And finally, you could have chlorination at C6. Remember, C6 is not, chlorination at C6 would be different from chlorination at C1 and C5, even though the hydrogens at C6 are primary, just like the ones at C1 and C5. C1 and C5 are 2 carbons from this branch point, whereas C6 is only 1 carbon from the branch point. If instead of 3-methylpentane we had 3-ethylpentane, then chlorination here would be equivalent to chlorination here or here. But because here we're 2 carbons away from the branch point. Or sorry, I should say chlorination. If this is an ethyl group, chlorination would look like this, and we're 2 carbons away from the branch point here. That would be the same as chlorinating at this carbon or at this carbon. Now we have a methyl group here, not an ethyl, so we're only 1 carbon away from the branch point. So this chlorination here at this C6 carbon would yield a different product, a distinct product, even though it's a primary chlorination product, just like the result of chlorination at C1 and C5. Okay, let me erase this. Erase this here. This was just a hypothetical scenario, it was related to this problem, but it was a different compound. It was if we had an ethyl group at C3 instead of a methyl group. Okay, so what's the distribution of these products? That's ultimately what we want to find, right? So to figure that out, we have to figure out how many abstraction of how many possible hydrogens. How many possible hydrogens are there that could be abstracted to give each of these products? To give this product here, you could abstract 3 hydrogens at C1, any of 3 hydrogens at C1, or any of 3 hydrogens at C5. So that's 6 hydrogens for this. For this compound here, you could abstract, and these are all primary hydrogens. So let me write 6 primary hydrogens. To get this product, you could abstract either 2 hydrogens at C2 or 2 at C4, and these are secondary hydrogens. This 2 plus 2 is 4. So here 4 secondary hydrogens. To get this tertiary chlorination product, the only hydrogen that you could abstract is at C3. So there's just one, and it's a tertiary hydrogen. So I'll write 1 tertiary hydrogen. And to get this product, you could abstract any of the 3 hydrogens at C6. So any of 3 primary hydrogens. And as we did in the chlorination of pentane example, we multiply the number of hydrogens by the relative reactivity. So here we have 6 times 1, because relative reactivity to chlorination of primary hydrogens is 1, is 6. And here we're dealing with 4 secondary hydrogens, so we have 4 times 4 is 16. And here we're dealing with 1 tertiary. So we have 1 times 5, and that's 5. And here we're dealing with 3 primaries, so we have 3 times 1, which is 3. So then we add up all these numbers. So we add up 6 plus 16 plus 5 plus 3. That gives you 30. So 6 out of 30. This comprises 6 out of 30, and that's 20% of the product. So 20% is this product here. We have 16 out of 30. So 16 out of 30. 16 out of 30 is approximately 53%. So 53% is this product here. This one we have 5 out of 30. So here, just draw an arrow. 5 out of 30. That's about 17%. So 17% is this product here. And here we have 3 out of 30. And that's 10%. So 10% is this product here. So we multiplied the relative reactivity of each of the hydrogens by the number of hydrogens there. We summed those products up, and then we divided each product by the sum of products to get the percentage of each product. And this was an example where our alkane had like several primary hydrogens, several secondary hydrogens, and tertiary hydrogens, and actually the tertiary hydrogen was here. And this was interesting in another way because there are two types of there are two groups of primary hydrogens that were not equivalent to one another. The ones on this carbon were one carbon away from the branch point, while the ones on this carbon and this carbon were 2 carbons away from the branch point.